So good morning, everyone. Thank you for coming, first of all. And also I would like to thank the organizers for this really nice QIP and for this great opportunity I have now to share my work with the community. About myself, I working at the University of Valencia, and the work I'm going to present here is a joint work with Carlos Palazuelos and David Pérez García, both of them at University Complutense in Madrid. Well, so the first thing I would like to do is make you understand what is this title of our work. And the first thing we are going to discuss is, well, this is not working, I don't know why. But okay, the so-called no programming theorem. So this no programming theorem is a no-go result, which was introduced by Nielsen and Chuan more than 20 years ago. And it spots on some limitations we have in quantum theory to program quantum operations in a memory. So I will make more precise this statement now. But let's first focus in the classical case. Now it's working, yeah. Okay, so put in your mind a general situation of information processing in a classical world. So we get from some source some piece of classical information, a bit string. Here. And then we put this classical information into our computer and process this information by means of some function f, so our program. So this is completely generic. And now the term programmable comes into this picture, requiring that we must be able to program this function f in some memory of our machine, and throwing also this information to our circuit as another input of the computation. So, okay, resuming, what a classical programmable processor do is computing some logical function, a program, on an arbitrary input data, and what we require is that we are able to encode the information about this program we want to apply in some memory of our machine. So let's do quantum, this picture. The first thing we do is replacing our classical input information by some state here. This notation here stands for density operators on some Hilbert space, H. And then we process our quantum information with some quantum circuits. And the goal of the computation is applying some unitary on our input state. So now the role of the program in the previous picture is played by some unitary. So how do we do programmable this sort of circuits? So what we require now is that we must be able to program this unitary in some quantum memory and throw this memory register also as an input to our computation, right? So the aim of a programmable quantum processor is computing a unitary operator on an arbitrary input quantum state, any density matrix here, encoding the information about the program we want to compute in some memory, quantum memory. And here I fix some notation, so I will refer with D to the dimension of the input register and with M to the dimension of the memory register, let's say. Fine. So, okay, these objects I'm introducing here, programmable quantum processors, maybe are not very practical, but they turns out to be a kind of fundamental object. So, because they appear in many connections in quantum information theory, and I argue that studying them is also interesting to study maybe a bunch of problems in quantum info. So then let's begin the study of these objects. The first question we must ask is, okay, I introduced some programmable quantum processors. Now I'm gonna make it universal in the sense that we want a quantum circuit which is able to compute any unitary operation, our input state, encoding this unitary in some memory as before. And we wonder if these objects exist. So can we build a universal programmable quantum processor, UPQP, from now on? And the no programming theorem tells us the answer to this question, and the answer It's not. That's not possible. So if you want to build such a machine, you need an infinite dimensional memory. This is a sort of elementary result, and is the result I was referring to the no-programming theorem originally stated by Nielsen and Chuang in this work. So what do we do now? What we do is relaxing the model we just introduced. So we are now going to talk about approximate UPQPs. Since the strict model is not implementable, let's try to relax it. So what is an approximate UPQP? The picture is again the same, but now we demand at the output of our circuit just an approximation to the ideal state we wanted to get. Okay, so to show that this new notion of approximate UPQPs is not empty, I will show you just a couple of examples. So the first example comes from considering the standard protocol of quantum teleportation. In quantum teleportation, we have two agents, Alice and Bob, and then they want to communicate some quantum state psi without using directly a quantum channel. So they just use a classical channel to send some information and some entangled resource. Okay, if they share the maximum entangled state, we know that if Alice measuring the best state in her part of the system, then the output of this measurement tells Bob which is the correction he has to apply in his part of the system in order to get the original input state psi. Now let's turn this protocol into an approximate UPQP. Imagine that we want now to apply some unitary U in our input state psi. What we do is encode this unitary in the entangled state that the two agents share. And then the encoding is just as simple as applying this unitary to Bob's part of the entangled state. So then we perform again the same protocol. Alice measures, and suppose the case in which Alice obtained as an outcome of her measurement the outcome associated with the trivial correction at Bob's sides. So then, in this case, with some non-vanishing probability, Bob already gets what we wanted, which is just our input state with our unitary applied to it. So we have here an approximate UPQP indeed. Another example comes from the case of port-based teleportation. Okay, in this situation, we have a similar goal as before. So we want to transmit this state here to Bob using some entanglement and some classical channel between them. Okay, now the players share a tensor product of n maximally entangled states, and it was shown by Ishizaka and Hiroshima in 2008 that there exists some measurement in Alice's part of the system, such that the outcome of the measurement tells Bob in which of the entangled state that they share he must to look to find an approximation of the input state we wanted to transmit. If we follow a similar strategy as before, in order to turn this into a UPQP, we again encode the information about our unitary in the entangled resource that the two agents share. So now we again perform the protocol, and at the end of the protocol, we here obtain an approximation to the input state with this unitary program applied to it. So this is what we wanted. Okay, so indeed, approximate UPQPs exist. Maybe we know that the strict model is not implementable, but the approximate one it is. And the question we want to ask in this work is, okay, what is the optimal memory dimension I can use in order to build an approximate UPQP achieving some error epsilon and for some input dimension D? Okay, so this is the question I want to answer or partially answer in this work. And to get further into this question, we first need to formalize the discussion we have done so far. So let me define formally this object I'm going to work with. So first of all, a universal programmable quantum processor, UPQP, is just a quantum channel P, such that for every unitary on our input state, there exists some memory state, such that the application of our quantum channel to the composite system input tensor memory applies in the input part of the system, just applying our desired unitary. So now let's give an approximate notion of these objects. And the approximation, so the closeness notion will be given by the diamond distance here. So again, we have that a quantum channel now is an epsilon UPQP. If, again, for every unitary on our input state, there exists some encoding in the memory space, such that the program, the quantum channel applied to this memory state is close in the diamond norm to the ideal channel, which applies just directly the unitary in our input. So if we come back to our examples and we consider these definitions there, we obtain that in the first case we had an epsilon UPQP with some very efficient memory consumption, let's say, but with a very poor error, which goes to 1 when D grows. In the case of pore-based teleportation, we indeed are able to achieve any arbitrarily small error, but the trade-off is that we need a huge memory dimension to consume in our protocol. So now we are going to study which are these kind of trade-offs between these two parameters, and the memory of our machine, let's say, our epsilon UPQP. So, well, I remind you the question we want to ask. So, we are wondering about which are the limitations on this function M in terms of the parameters epsilon and D. I will focus just on two particular cases in which we consider first the input dimension D as a constant, and we look at the scaling of this dimension M with the error parameter epsilon. And then we are going to study the same thing, but the other way around, right? So we consider epsilon as a constant. We wonder about what is the dependency of this function M with D. So known results, or previously known results can be summarized in these two gaps between lower and upper bounds. And we see here that in both cases, we have here exponential gaps. This meaning that even when these objects are some important objects in quantum information theory, we have a quite poor understanding of them. And this is what we are trying to improve here. So in this work, firstly, we give a new upper bound for the first case, which essentially close this gap, or at least reduce this exponential gap, just to a polynomial versus polynomial question. And then the main result in terms of techniques of this work is a lower bound for this second. Okay, so a lower bound which in this second case again close this gap here with this exponential gap here to again an exponential versus exponential. So we are now we have nearly optimal knowledge about this object. So just let me state in a theorem these two results I already said. So the first, so in this talk I will focus in the case of unitary epsilon UPQPs, and then what we show is that any unitary epsilon UPQP, unitary means that our channel is a unitary channel, must satisfy this lower bound, which corresponds to the last result I'll tell you. Okay, this theorem comes with a moreover, let's say, which is a construction which gives you this upper bound for this function M. So in this talk, I will just focus in the first result, which is the main result of our work, as I said. And in the minutes that I have, I will try to explain you how did we get this lower bound here. Okay, the key ingredient in our proofs is understanding these objects, epsilon UPQPs, as embeddings between some linear spaces which inherit some properties from this property of a channel being UPQP. So let's first think about an arbitrary unitary channel acting on a composite Hilbert system. And what we do is putting any of these channels in correspondence with a linear embedding between these two spaces. Okay, here I'm denoting with S1 of H the space of operators on our Hilbert space H when we consider in this space the trace norm. Okay, and in the second space, B of H will mean just the same space of operators on a Hilbert space, but endowed with the usual operator norm. The specific structure of our embedding, defined by this unitary V, looks like that. And let me comment that this correspondence here comes from a very well-known completely isometric identification between these two spaces. So the space of bounded operators on a composite Hilbert space as our V, and the space of completely bounded linear maps between this space S1 of H and B of HM. So in particular, once we know this completely isometric identification, what we get for free for our embedding is that this embedding indeed is contractive, and indeed it is completely contractive. So now let's focus our attention in the case in which our quantum channel is in addition an epsilon UPQP. So we have this correspondence, and now we also demand that this channel has this kind of programmability properties. We show that these properties now translate into the properties of this embedding as a sort of an isometric property. So for any unitary epsilon UPQP, the embedding we have just constructed verifies this chain of inequalities, which in essence tells you that this embedding essentially preserve the norm of any element in this target space. Up to this correction, which depends on our parameter epsilon, another thing. For completeness, we also shown a kind of a converse of this theorem, showing that if you start with a completely contractive map between these spaces, such that the map verifies your nearly isometric property, then you can construct some epsilon UPQP with the parameters of your epsilon UPQP depending on the parameters of the embedding. So we have here a characterization of this object between as a very, let's say, well understood object in the mathematical side of the picture. So now, the following thing I will do is exploit this characterization to prove our lower bound. So we begin considering some channel, which is a unitary epsilon UPQP, and thanks to our theorem 2 of the previous slide, I know that I have some embedding between the trace class operators on H and some subspace of the space of bounded operators on our memory Hilbert space. Okay, the theorem 2 told us that this embedding was indeed an isomorphism with this isomorphic constant, which is controlled again by the epsilon parameter of our epsilon UPQP. And the powerful of our techniques is that with this line, we are almost done with the proof. So in the following minutes, I will show why we are done. But the key observation is that the existence of this embedding with this property here indeed implies strong restriction on the spaces involved in the embedding. So we are going to look at these restrictions, just looking at the geometry of the Banach spaces which are involved in this embedding phi. Okay, we found the correct tool to deal with this question in the theory of type and cotype of Banach spaces. So now I'm going to introduce the notion of the type 2 constant of a Banach space, which will be the essential quantity we are going to study in order to get our lower bound. Well, so for a given Banach space X, we define its type 2 constant as the best constant I can put in this inequality here in order to make true the inequality for any sequence of elements in our Banach space X. Okay, I comment very briefly that what we are comparing is, let's say, an expected value of the norm of linear combinations when I put here random signs, uniformly distributed. And we are comparing the expected value of this norm with the sum of the norms of our original element in X. I don't have enough time, I think, to spend in this notion, but as a very easy example, you can see that when you focus on the case in which X is just a Hilbert space, so this is the Euclidean case, an application of the parallelogram law gives you this inequality with constant equals 1, and indeed it turns out to be an equality in this case. And this property is characterized in Hilbert spaces. So any Banach space with this property, so satisfying this with an equality here and a constant 1, is symmetrical to a Hilbert space. So what we are going to measure in some sense is how our spaces are far from the Euclidean case. So once I introduce that, to conclude the proof, I just will need two properties of this constant, which readily follows from the definition I give you. So the first property is that these type 2 constants are preserved by subspaces. So if I consider a subspace of my Banach space X, then the type 2 constant of the subspace must be lower than the type 2 constant of the space. The second property tells you how this type 2 constant behaves under linear isomorphism between Banach spaces. So if I have some isomorphism between X and Y Banach spaces, I know that their type 2 constants are related by this inequality here. So now we come back to our proof. Remind that we have this linear isomorphism between this space and this subspace of B of H with this isomorphic constant. And now applying these two properties, I give you in the previous slide, we attain this chain of inequalities here. And now to conclude, what we do is just estimating this type 2 constant. So these are well-known objects in the theory of local Banach spaces, and indeed we can get these estimates for these constants. So introducing these new inequalities here, we obtain our bound. Okay, so to conclude my talk, I just will mention some final remarks. Okay, I'm a bit fast, but it's okay. So I will do some final remarks. So summing up, we have closed, or we have improved a lot existing gaps in the understanding of optimality of epsilon UPQPs. And we did it essentially in the cases in which the parameters d and epsilon were considered separately. So one can ask, what happens in more possible scenarios, so in which I don't enforce one of these parameters to be constant? And it turns out that we can get some information about, we can get some information from our theorem 1, just considering, for example, the case in which our epsilon UPQP with a memory of polynomial size in the input dimension d. In this case, you get this corollary which restricts the accuracy of your possible epsilon UPQP, which is efficient in the sense that use an efficient amount of memory. And indeed, more or less the behavior that this corollary enforces in epsilon is similar to the behavior that we obtain in the example of standard teleportation. So we are not far from being optimal, given this bound here. Yeah, okay, next comment is that, as I told you, UPQP appears in relation with many problems in quantum information theory. So can we use the results we give in this work to obtain some new information about other problems in quantum information? An example is given by port-based teleportation. So if you use our lower bound, which were deduced for these objects, universal objects, if you use it to bound the resources you need to consume in port-based teleportation, you already obtain for free some bounds to this entanglement consumption of the protocol. So in the next talk, Christian will tell you about better bounds, okay? But the point here is that we obtain this bound for the entanglement here just with very little effort, or let's say just importing as a black box our lower bound to this context. So can we make this to in other problems in quantum information theory? So I don't know, it's a question for further research, let's say. And yeah, as a final comment, I will sum up that we characterize these objects that we studied as an embeddings between some normal spaces, and we use classical tools from local Banach space theory in order to get the results that we wanted. And the message I would like to bring here is that I hope that these ideas and techniques that we use maybe are useful also in other contexts in quantum information theory. But this is again for further research. And let me thank you again for your attention. Just if you want to look for further details, just go to the paper. Thank you.
Yeah, thanks, Alexander. We have plenty of time for questions? Okay. I'll run back to...
Yeah, thanks for the talk. So you talked about two different approaches for approximate programming, basically. Teleportation, port-based teleportation and different approach. I just want to say there is a third approach where we call it the universal quantum emulator. It uses copies of the output state of the unitary, several copies to emulate the action of the unitary, basically. And I think it might be interesting to compare your bounds with the bounds that is obtained by using that algorithm.
I'm not aware about this algorithm.
There's a paper that I've written which says like, I can send you the paper later.
Okay, but the key point, I would say that is considering how the information about the unitary you want to apply comes into the protocol.
Yeah, it's through the quantum state that basically sample.
Yeah, but I mean the protocol is universal for any unitary you want to apply. Yeah, okay, so then I would say that probably you can use some of the information we got in here in order to bound, to get some bound.
Yeah.
There's here.
Sure, I can send you the paper later.
This was the question. Yeah.
Yeah, I just want to say. I mean, it might be interesting to look at your
sure.
bounds and compare. What,
yeah. Okay. So we can discuss it. Yeah. Thank you.
Hi. I would like to ask whether your techniques could be used also for the exact case where epsilon would be equal to 0. Is there some possibility to use the same techniques?
Yeah, sure. Actually, the characterization give also proves the original no-programming theorem. But okay, the proof is much more involved. But you know that you cannot have an exact isometry between these two spaces.
Okay, but what I have in mind is the case where you don't go for approximate processors, but rather for probabilistic processors.
Sorry.
Processors.
Yeah, sorry. I didn't understand before. Okay, so the case is that both cases are included in our notion of approximate UPQP, because in both cases, if you have a probabilistic machine, you can also obtain a bound on the diamond distance between this probabilistic channel and the ideal channel you want. So you can apply also all these, let's say, all these all these techniques and all these results to the case of probabilistic UPQPs also. Yeah.
But I mean, I have read the paper and I haven't noticed that. So let's discuss afterwards.
Yeah, sure. Thank you.
Okay.
Yeah, I agree.
So sometimes you put this mysterious C constant, and could you tell us how big it is?
Yeah, it's reasonably low, so you can take it as 4 or so.
4. Okay.
Yeah,
Cool.
so it's not a crazy thing. It comes just from the estimates you give for this type 2 constant.
One more question down here.
Yes, so I think there is another no-programming theorem for POVMs instead, right? Do you know all this? So do you know if this technique can be applied to that?
Not in principle, I would say. But yeah, there is related situation when you want to program just measurements, not unitaries. And what is true is that any UPQP can be transformed in a programmable measurement, but not the other way around, okay? So if you have this in mind, you can export some information from one picture to the other, but the relation is not in the both ways.
Okay, I think we have time for one more question, a few more questions if there are any. Well, let me ask, I think maybe my question is the same as the last one, or similar. Are there any restricted classes of unitaries that you can also say something about?
Yeah, exactly. So let me go back to the definition of this. Okay, the key point here in our proof is that the bound comes from some estimates on your type 2 constants. And indeed, you can estimate this type 2 constant for specific elements in your spaces. So restricting, okay, if you find good enough constants for just, let's say, a fixed amount of vectors, then you can associate these vectors in your input space with some unitaries applied to any state. And then you can improve, or let's say get the same bound or maybe different bounds, but for restricted families of unitaries. And you can do that. There is a comment also in the paper. Yeah, and an interesting family is indeed the family of unitaries, of diagonal unitaries, which is a family of 2D unitaries, right? And in this case, the same bound here applies. So it turns out that in this case, for this family, you cannot do any better than just storing any unitary in one orthogonal state. Yes.
Okay, let's thank Alexander again.